learned, what we discussed before our break. Now we had some time to let it settle. Are there any questions that you would like to discuss?
Sir, in the previous lecture, one assumption was there that spatial data is independent on each other. But sir, I have one question, sir. If there is a undulated land, there is sloping. Suppose this side is downward, this is upward. So the runoff will be more. The nutrient will get carried with the runoff. So the soil there, and if you compare the soil from the lower portion, the fertility will be vary. So due to undulated land, this land is getting more yield in comparison to the higher elevation. So this is going to affect the lower portion of the field.
Yes.
So how they can be independent in this case?
They cannot be independent.
Yes.
So first of all, did everybody hear the question? Yes, good. If not, then show up. So we have a slope situation in the landscape, and at the higher landscape positions where more fertile soil is eroded to the foot slope, at the higher position, the crop yields are lower than at the bottom positions for many different reasons. Fertility, more water in the bottom, so we all know that process. So from top to bottom, there is, if we could measure the yields there would be a strong increasing yield trend. And a trend in the data shows no independence. All the data are very strongly dependent. We will see that phenomenon addressed when we deal in the next lecture with autocorrelation. So I have elevation data that reflect the same phenomenon. So what do we do in that case, and what does an autocorrelation or a range of correlation manifest in that situation? So no, there's no independence obtainable in that case. We can statistically produce an independent data set from that if we detrend the data. And we then subtract the trend from those data until we have just scatter of the data, which is the signal minus which is the data value minus the trend. Then more or less random data set. So right now that answer may not be very satisfying, but when we get to it in the autocorrelation chapter, we will discuss that again. Okay, thank you. So before the lunch break, or was there any other question? Okay, before the lunch break, we started how we can sample a process. I personally think we are paying not enough attention to that phenomenon. We measure, we use a method, a tool, because it is given to us, and we don't worry too much about how do we really measure it, and what is your intellectual connection to the term scale? When you hear the word scale, what are you thinking about? What scale is? Scale is?
Spatial or temporal.
Yes, scale is spatial or temporal. And what is your first association with it? So of course, dimension, size, leg size, or length size. So scale, you are talking about large scale and small scale, right? Yes, that is the classical paradigm that we connect with scale, but there are in fact more components to scale. And there are two hydrologists, Blöschel, I think he is from Austria, and Siva Palan, I think he is from India. They have written a very nice paper on the on the scale triplet. And that is what we want to look at next. And then we want to look also at the term representativity and association. So the first is the scale triplet. This is a nice, simple diagram that shows it. So in what we just talked about, large scale, small scale, that is what we usually connect with domain and extent. That's the size of our observation unit. And that can go from a continent through region, through field, through plot, and even a computer CT scan of a soil sample can also be considered as with its own scale, the size of the domain. What is important, all the statistical analysis we do, they depend on each of the three components of scale. So there's not the answer oftentimes. We like to have one answer, but no, the answer varies with any of these three scale components, and when we modify one, then we change the answer already. I don't see any excitement. That should make you excited, because that means job security. We have not even touched the basics with that. We as soil scientists, or also as agronomists, as engineers, as hydrologists, geologists, we should study what the process, how the process changes, how the description of the process changes when we change any of those three components. The second component is the spacing, the resolution. That's what we were referring to earlier when I said here we have these about 50 by 50 centimeter tiles, and we go from one to another. So each of these 50 by 50 centimeter tiles is a way we take the center point from it. That is the separation distance, or called also spacing or resolution, or later when we look at a function of a variance versus that distance, we call that distance also lag. You have perhaps heard of lag when you have looked at a semi-variogram or so, but that is the lag distance, the separation distance. We will explain that term in detail. So that's the second component of the scale triplet. The third component is the support or the integration volume. That is the size of the unit that I look at, and makes a big difference. If we look at a value that represents that 50 by 50 centimeter, or a value that represents 4 of those together, or the whole room, or a tiny, tiny bit. So that's the support and integration volume. And a lot of processes cannot easily be determined if our support or integration volume is too small. And some we can technically not sample at a small support volume. We can only measure them at a large support volume. Here's one example. So you want to find the relationship in a farmer's field between yield, grain yield, and clay content. You have a big combine harvester with a yield monitoring system. You know that. So let's say the combine harvester has a cutting table or header width of 10 meters, That's not the largest one. There are even larger ones. But let's say that combine drives 10 meters and it takes a measurement just by a chance. I say when it has moved 10 meters, then it gives us one data point on the yield map, the data point and the coordinate. So we get that for the whole field. And now we want to know what's the variability in that field of yield and how is that variation related to soil clay content. We know we measure 10 on a 10 by 10 meter area or support size. We measure yield. Now what do you do about clay content? Do you measure it also 10 by 10 meters? No, you can't do that, right? Dr. Kritika would really not let you go out and bring all the soil back that you collect in 10 by 10 meters. No, of course not. It has to be technically handleable. So over a 10 by 10 meter area, what would you do to get a good representative clay sample? You would start with your intuition. If you don't have intuition yourself because you are early in your career, then you would get experience from a pedologist, or you could run your own test. So people have done that. So you could go over a 10 by 10 area in different parts of the field, and you collect within that area many samples, mix them, and then you have your mean value. Or if you want to be very thorough and do a systematic investigation, then you take individual samples over that area, and then you do not mix them into one bulk sample, but you analyze them individually, and then you do the mixing afterwards in the computer by averaging their individual values. And then you can say how many samples you need. With increasing number of samples, the variance will go down and then stabilize at a certain number. So by further increasing your measurements, you will not change the mean and not change the variance. So that is then representative. So often we do not take the time to do that systematic study. How many samples do I need from that 10 by 10 meter area? So we use our intuition, pragmatism. It has to be done in decent time because a PhD student has only 3 years to complete their degree, or you as a scientist, you need to move on. So you sample, let's say 2, 3, 4 samples from the area, mix them, and then bring them home. And then you go to the next square. So that's where you cover the area that you have harvested, and then you can run the correlation with clay content. But keep in mind, both variables that we correlate have completely different, we sample at completely different scales. The domain overall is the same. The spacing is also the same, but the support integration volume for both variables is different. That's what we have to keep in mind. So here is a little cartoon on a real process. This is a true process. We get all that scatter here in the data, and overall we can already say this is a structured process. We have trends in here, then we have ups and downs, and the local scatter is always way smaller than the overall variation. So that shows us we have some dependency. We sample this real process, which makes it look like this. So every little wiggle is covered with our sample, our core. Now, in many situations, we cannot do that because that's way too much work. We cover the same domain with a smaller set of samples like this. So it's the same process, but because of manpower, lab capacity, equipment, time, we can't do the intensive sampling. We sample it this way. And what is the effect of it? We get the overall behavior of the data, but a lot of variation, oscillations that have a smaller scale, we lose those. Whether or not that is good, we cannot say, because in reality, we don't know all these. So it's the best way we can do at the time. And if we think we miss something, then we have to go into smaller units. I'll talk about that in a moment. Here is another way. So now we vary the support size, the sampling volume, going from a small sample to a larger one. So in this case, we not only sample this point, but we include also a lot of scatter in the process here and here and here. That will modify the mean value that we get from each of these samples for that particular location. So that is what I said how each component of the scale triplet will change our measurement value, our measured value. If we cannot do the intensive sampling and we have no clue about the process, we cannot capture the whole field with narrow sampling, but we are eager into getting it, then we have something that the geostatisticians call nested sampling that leaves us some opportunity to find out about these small scale characteristics. So that is a good compromise for getting the small scale wiggles in here with a decent effort. However, we then miss out on all these locations here, but we know the statistics over these smaller scales. So if we have only the capability of collecting samples every 4 tiles, so this one, then 2, 3, we cannot sample, but this one, and then again this one, that might leave us with this range of representativity. We said earlier 3 tiles, that might leave us with a random data set. So in order to know, oh, what's going on there at a smaller scale, do I miss something here? Then I can say, okay, here I sample all 3 of them, then I leave some area 3, and then I sample again 3. That gives us the information about the closer neighboring distances. Then when it comes to sampling 2 variables, that is shown here in this image, we have the same program, and then we have another overlying variable here by the black line. Some of the wiggles are similar, show the same behavior, but some are also leaving it out. So what we said for the 1 variable is true also for 2. We can sample all these wiggles here, and then we may even try to find a relation between these and these wiggles, and then try to interpolate using these, try to interpolate the process here. That, for example, can be done with co-kriging. So finding out the relationship in certain subdomains of the data series, identifying their variability structure, and then we can regionalize observations, transfer them from one variable to another. A very popular example for that is, for example, clay content and electrical conductivity. Has anybody of you run that analysis? Has anybody of you measured electrical conductivity, for example, with a Veris instrument? That's a geophysical machine. No? Okay. Well, we will look at data of that during the further process of the course. Do you have any Do you have any experience with data that are so difficult to handle that one sample will not really tell you? So cases where you really need, in order to have a good point estimate, where you have to collect either many samples or one very big sample. Do you have any example for that from your experience, from your field work?
Maybe some other radiations are itself statistical in nature.
Mm-hmm.
Needs repeated measurements from standard deviations.
Repeated over time? Okay. Mm-hmm. Yeah, thank you. That's a good example. Another example would be mineral nitrogen. Has anybody of you sampled mineral nitrogen in the soil? I've done it a lot, and so one sample is no sample. We have, in order to get a point measurement, we have to do at least 4 cores into the ground. So anything less than that will give us with a random number. And we have done systematic tests with individual core analyses, and they have confirmed this idea. So mineral nitrogen is really a very difficult variable. Though it is very important. Another example that relates to that clay content and combine harvester. We have 2 processes, and we have to sample them with different sampling volumes and then can relate them. So there's no rule that says, oh, if you sample one variable at one big volume, you have to sample all co-variables at the same volume. No, that's not true. It's all allowed, but we should be aware of it, what we are doing. In statistics, like in all other things, everything is allowed. Everything is allowed to do as long as you say exactly what you do. And then we here use this one variable with very large volumes, but this one would give us a hard time to reproduce the process of that second variable, because too much of the wiggles are disappearing into this one volume. So that does not work out. Another topic that we want to talk about, we have now mentioned it so many times, this is one of the keys in spatial data analysis. It was the beginning, so to say. This is a semi-variogram. Has anybody of you seen a semi-variogram before? No? You have, yes. So we will go into detail of a semi-variogram, how it is constructed, how it is computed. Here I only want you to give a very short glimpse so that you get the idea and that you get eager to learn it. On the x-axis, we have plotted the lag distance, which is the distance by which neighboring samples are separated. This variogram, for example, is based on a collected data set of soil microbial respiration that my colleague Stefan Wirth and I took some time ago. Our sampling distance was somewhat about 5 meters. And so we had a long transect with 50 locations. And this variance showed the variation for all neighboring samples that were 1 sampling unit, so 5 meters apart from each other. All those. This value, for example, at 15-meter lag distance at 13 lag distances, so 13 by 5 is 65 meters apart. So you can the farther apart the samples are taken, the less observations go into such a semi-variogram coefficient. And at some point, at some distance, the variance will not increase with increasing distance, but it will fade out on a plateau. So the variance from here on is not anymore changing, and that shows statistical independence. Up to this range of correlation, the data they vary, we say, with structured variability. That means we see neighborhood relationships that we can very well use into an interpolation calculation. So this is structured variation and this is random variation. And I want to refer back to what we said about randomized experiments. Observations are independent from each other. Have you seen ever a paper in the journal that shows ANOVA results, a table? Have they done the test on spatial independence? I've not seen it. But that's what that analysis requires. This is disregarded. The experimental conditions need to be this way. Observations are independent from each other. What is all that important for this neighborhood relationship? For many measurements, it is the fact that we cannot take measurements of two variables or the same variable at two different times at exactly the same location, because our sampling may be destructive. We can never get back to the same point. One example is soil water retention curve. You know what that is? Many of you do. So here we measure soil water retention curve in the field. At one location, we measure soil water content. For example, here with a nutrient probe that we lower down in an access tube, or with a diviner probe that is a frequency domain probe that I've been using a lot. And nearby, we install tensiometers to measure the matrix potential. And then we relate both. For different depths, we have the tensiometers. So they cannot be at the same spot. How do we know that the water content I'm measuring here and the matrix potential that I'm measuring here, that they are related, that they are within their sphere of influence, their statistical sphere of influence, not the physical. The physical sphere of influence is something different. Neutron probe, what's the physical sphere of influence for that? There's a formula that includes the water content in it, but it's about 30 centimeters maximum. And you have your tensiometers farther away than 30 centimeters from a neutron probe. Statistical range and physical range of a capacitance probe is even smaller, about that much. So how can we then relate matrix potential to water content measurements? Here another observation. What spatial resolution? So this shows a land surface, and we go over it with a satellite or a drone or whatever remote sensing tool we have at hand. What spatial resolution for water content measurements in space and time can we make? How many point observations of water content we need to take to be spatially related to one remotely sensed pixel? We call that data aggregation. So here we have one pixel that the satellite sees, and we put out there soil water probes, or we collect water content samples. How many do we need to take in order to create one value that we can correlate with the pixel that is the pixel observation that is taken by the satellite. Soil moisture sensing has made huge progress, but I don't think we have followed down this track to answer this question thoroughly, and I don't think it is technically feasible. I don't think so, personally. I think we need to treat our satellite determined water content as a different variable. We cannot take it, we cannot accept it and treat it like a physical soil water content measurement that we get from a sample that we put in the drying oven. This is over a much larger area, and we just need to take it as an indicator. I like to have this comparison with the gas gauge on your car. I drove, when I was your age, a VW Beetle. And the full gas gauge, well, it stayed full until it showed full until the tank was started to come down to about 75%. Then the needle would move. The needle was not correct, and it said at some point half, and then quarter, and then empty or reserve. But that half and quarter never was correct. The range of the needle, that distance on the meter, said so, but it was never correct. However, I knew that, so I knew when I was half down, by far the gas filling was not anymore half, it was way lower, so I soon had to go back to the gas station and fill it up. And in the same way, I knew that when the gas needle did not move in the very full range for a long distance, oh, I am driving very economically. No, that was not the case. It was just the technicality of that gas gauge. So we have to learn to read our gauges that we use and then treat them as variables. That's what I think about land surface observations of soil water content. It's a good indicator, but we cannot treat it in a Richards equation or Darcy equation. So going back here to this diagram with different mapping units, I want to say there's no justification for the assumption that any functional behavior in any of these same looking mapping units, such as hydraulic properties, remain constant within each mapping unit. No, they change within each mapping unit. Nor that functional behavior is the same from this mapping unit with the diagonal lines to that one with the same pattern. No, it is not the same, occurring at different regions within the domain. The link between the spatial distribution of function, for example, fluxes and soil mapping units, remains a challenge. So we cannot say, I've seen that, or I sample, in order to know the mineral nitrogen distribution in that big field where we have these different mapping units, I go here, and then since this is the mapping unit with the little bullets in it, this is the same there and there and there and there. That's not the case. So those units are made for certain purposes, but for a lot of functional considerations, they are invalid. We can appreciate the one thing for its purpose, but we also need to know its limitations. So from a soil physics perspective, without knowing the spatial representation of locally determined soil hydraulic state variables and properties and their covariance with fluxes, estimating the pattern of soil water fluxes remains arbitrary. So they differ even the same mapping unit. The functional and quantitative representation of soil mapping units remains insufficient. And what is it from your perspective? So here you also can fill in the blanks. Once we got a little further with the lectures, then you can, or you will now start thinking about your own measurements that you are taking and what's their value and where are their limitations when it comes to mapping and categorizing. So in this course, we will look, after we have gone in the next lecture through some introductory general statistics to bring us all to the same page and for us to see how spatial statistics are really related to the very ordinary statistics that we know about, mean and variance. We will have that, and then we follow with autocorrelation, cross-correlation, and the rest of these properties that Professor Kothari read this morning in her introductory speech here. We will learn about all these techniques and methods, and here are a few cartoons with them. So these will be the basic figures that we will look at for data, one-dimensional, so transect observations, how they behave in space, and then we will compute the autocorrelation function. And I will explain, of course, we will all learn what an autocorrelation function is. And this computation, for example, can be done in R. We will also learn that in an exercise. We will then go over to the twin brother or twin sister of autocorrelation, that is then for two variables, the cross correlation, and we will learn how the cross correlogram starts with a classical Pearson correlation coefficient, and then we have two branches here, the positive and negative legs, when we shift data series against each other to identify if I measure variable A here, to what distance is it still related to a measurement of variable B. So is it only next neighbor or the same location, so to say, or can I shift both a certain distance, like the water content and the tensiometer, and they are still related to each other? That's what the cross correlation function tells us. Then we will go into semi-variogram calculation. This is the same variogram that we just looked at a few minutes ago. These are the original data, biomass in soil microbial respiration rate. We will also look at semi-variograms, how they can be used for kriging. Kriging, a method of spatial interpolation. And we will also use then cross semi-variograms of two different variables to do co-kriging. That means that gives us the opportunity that we can have one cheap measurement that we can get in high density, like the EC measurement, electrical conductivity, with a vehicle. Gives us a day riding a tractor and recording measurements, and then relating it to less dense observations of soil clay content. We will also look into variations that are occurring on a cyclic basis, so recurring observations, and that's a field for agriculture anyway, perpendicular to the main tillage direction. We have always these cyclic behaviors, and they occur also naturally in time series when we look at temperature data of the air or atmosphere and then different soil depths. How can we identify their frequencies? We have also used that kind of analysis for explaining soil water storage in a field, clay content and yield variability in a farmer's field with co-spectral analysis. And then finally, we go into autoregressive state space modeling, where we describe in a simpler way than kriging the spatial association between different variables. And here's also an outlook on physically based equations. I will show an example for internal drainage experiments. So here I want to close up with this first set of slides by having us look at this diagram. It's a space-time scale diagram. And many of us, so before I got into this, when I started studying this after my PhD work, I found this a very helpful diagram to get an idea what I'm doing at all with my samples and my processes. So this is sort of a map for linking different disciplines that work in a similar area, but on completely different scales. That's a very difficult thing, not only for scientific reasons, but also for personal reasons. The thoroughbred soil physicist who looks at surface phenomena, micropore phenomena on transport, capillary forces, that person ticks different than a physical geographer who looks at the landscape, who finds that as his paradise, and that's where the music plays. Everybody thinks, oh yeah, that's the scale. That's where the important things happen. Well, we need to somehow come up and link it. So I have looked here in this slide on soil-water related processes. And at some point, it may be a little sporadic, but I think you will get the idea. So here at this combination of square micrometer in spatial scale and second to minutes, that's where the solid phase liquid interactions happen. So in my discipline, a person like Denny Orr, you may know him from the literature, very famous soil physicist, or he has done fantastic things of solid phase liquid interactions. Then at the next larger scale, about square meter and day and a little more, have Darcy phenomena, Richards equation, and preferential flow. Some of you may have heard about Nick Jarvis, who is one of those who have first put preferential flow and bypass flow into simulation models. So his domain would be this one here. And it varies. It's not a tight scale, but you get the idea. Then at the next larger scale, I think that is where I'm about most of the time. So the 10 by 10 meter and the weekly to monthly scale, this is where the researchers are interested in vertical water content distribution and associated crop and soil response and also drainage behavior of the soil. Crop water uptake, evapotranspiration, that's the scale where that thing plays. And still going up one more scale, balance components of the annual water cycle. Well, here we go to the hectare scale, annual scale on the time axis. This is for us of interest for irrigation and for many other aspects. And also seepage. We want to know land use, how does it affect seepage, and what the hydrological engineer of the city can expect in terms of nourishing the groundwater body for gaining drinking water again. So that is that scale. And then even at a larger scale, we look at the global water, the global climate and water cycle. So here you get it all across it. Interestingly, all these main areas, I call them for now playgrounds, where people working in soil physics and hydrology, so people that are in the farthest related to soil, water, and atmosphere, all these playgrounds are along a diagonal. There's not much happening up here and here. Well, I must say there was not much, because in recent years, we have explored other areas too. So we have now tools that can measure land surface water-related processes, regional evaporation over pretty large areas on, so to say, a daily basis. There are satellites now ET, I don't know its exact name, that delivers you evapotranspiration data on a daily basis for fields. I don't know how precise those are, and I wished I had more time to study those, but that is really a huge, fantastic development. And we can further build on that to improve our water management schemes. Another one that at the time when we wrote this book was very relevant here was the LiDAR scanning. I don't mean the surface LiDAR that allows us to produce nice and fancy digital elevation models, but the Raman LiDAR that allows us to measure the water vapor concentration over a field. And that allows us to identify the zones where evapotranspiration is down because the stomata shut off because of water shortage. That's very important to know. Well, that's technically very difficult, and you also have to follow safety rules. You cannot have people standing around when you shoot your LiDAR gun there because it affects your eyes. But now we have thermal infrared cameras that get a picture over a whole field, one snapshot, and you can see where the crop is suffering water and where not, before your eyeball can sense it. That's fancy. And in the other field that was, so to say, a little empty here, we now have soil management and soil structure and soil-water interrelations at these long-term plots that some institutions are sponsoring and fostering in their experimental setup. Not all, but if your institution does something like that, these long-term observation areas, that is a fantastic thing. My university does. We have experiments that are about as old as I am, so pretty young still. But these experiments allow, we have data for those, for nitrogen cycling, and we see the long-term effect of certain tillage and nitrogen management strategies. So I want to encourage you, when you go home from this course, either now or at the end of the week, here is my gift for you. These are the little gold nuggets. So you are all in different disciplines, as we learned when you introduced yourself. You can print this out, and then you can modify it. You can draw your own one, and then you fill in where you and your colleagues are working in. You know them. And then, so as I told you earlier, in my discipline, it is very hard to get together the, oh, I'm sorry. It is not easy to make all these people talk to each other. And probably you will never get somebody here from this patch talk to the global and climate water cycle expert. They are too far apart. But if you can manage it, that this guy here talks to this guy and to that guy, and then they interact with each other and identify how a scale transfer can be made between different space-time scales and what information is gained and what information is lost, then you have accomplished a lot. That's really important, that we, in our own playground, look at what other people do. We can certainly learn from them, how they approach their things. And remember, I told you about Nick Jarvis, the preferential flow expert. So you can measure it at this scale, but measuring it at this scale does not mean, and seeing that it's on a square meter basis and here on a daily to weekly basis, doesn't mean that these phenomena, preferential flow phenomena, are not of ultimate relevance for balance components of the annual water cycle, of the impact of land management on flow phenomena, and even on the global climate and water cycle. So even though they may be far away from each other, and the geographer will not know and not appreciate necessarily how we measure preferential flow, says, oh, that's small stuff. And the preferential flow guy will say, oh, the geographer, yeah, they think only in continents. No, my domain is here, 4 tiles, and then measuring using dye and following those flow paths. No, they have to get together and say what is important to use. For example, the geographer's work to extrapolate, to create a map on preferential flow phenomena. There's a common nail where this can be hung up and extrapolated to a larger scale. That sounds a little utopic, but it needs to be done. So here ends my introductory part for the course, and I'm then ready to continue with our review on ordinary statistics, but I first want to give you a chance to reflect and ask any questions or give comments on what we have discussed so far.
This is kind of
Scale triplet. So you were asking me, is this length, space or time? It can be both. So it can be an observation that we consider over time, or it can be an observation that we consider over a transect or even in a 2-dimensional domain.
support integration volume.
The support integration volume. Yeah, that's a good question. So I have several slides on support and integration volume that we will look at when we talk about autocorrelation. For now, so one example would be this mineral nitrogen example. We cannot, ideally, we would take 4 to 6 samples from an area of about 1 by 1 meter, 1 square meter. We cannot take the whole sample out, so we have to find a way to take subsamples and bulk them in order to obtain then a representativity for it. The other example was combine harvester. Yield measurement, 10 by 10 meters, one number. We relate it to clay content. We cannot take the same support volume. We just have to take one or a few point measurements and then try to relate those to the first variable that is sampled at a much larger support volume. So with each, deciding for a particular support volume will affect the answer. And we have to find a way that for the clay content measurement, in order to be the best covariate to yield, that we find a representative value for the clay content, a strategy to determine that. Most of the time it is pragmatism. So it is not science. I use myself a lot of pragmatism because I want to go to bed at some point at night. And we have to accomplish sampling of a larger area. So I use my best intention that I can, taking a number of samples that I hope will be representative of that 10 by 10 meter area, and do that over the same domain that we have sampled yield values.
So why I'm asking, my next question is On to the next graphs. Next one. Sizes of the circles are, they are relative or
The cycles were chosen here in order to manifest, to cover every little wiggle at the series. So there's no wiggle, no change in direction between these blue open bullets. It's always a straight, direct connection. So this is the finest resolution for this true process. You ask me whether we can quantify that.
diameter of the
So here we have larger cycles, we have not as many, and here now there's a lot of variation going in within it. So we can quantify the difference between the two by taking one sample here and then taking the large sample, and then we can still obtain samples, these little blue ones here, and yeah, here it is not quite large enough, and then we can compare them and we will find a difference in the answer. That's for sure. There's no final ultimate approach for doing that. I just put that out as an important topic in science that we need to solve. These are all considerations that we should take into account before we go out and sample. How big of a sample do I take? And also that decision is in most cases driven by pragmatism. So I have a colleague who wants to go out in this long-term experiment and take their samples. He's interested in spectrometric measurements on nitrogen and on bark density for soil organic carbon balance. So he wants to take these big ones, and that is certainly the bigger the better, but they will not allow him to go into this long-term experiment and perforate those small plots. The plots would be of a size here in this room, we would have about 4 plots. So they would not allow him to take in each plot 10 of these big cores. It's pragmatism driven, and you have to do it that way, otherwise you cannot run such an experiment. But the question is there, and that's why I think that should give us soil scientists and agronomists and all those in our areas of science that we are here, that should give us job security. And now, especially when we link satellite measurements with Earth observations, well, we can do now so much more. Something from a drone. So my technician is now working on his PhD degree, and he gets drone images from individual small corn plants. We are just beaten by the tremendous volume of data. But now we can follow every individual corn plant in the field, and we can have subsequent overflights, and we can see how individual corn plants grow, how tall they get. Well, what do we do with that information once we have it? We want to integrate it over decent areas that we can say, oh, this zone in this field is less fertile than that zone. So the questions we can now ask from these high resolution images are way different than the questions we could ask 10 years ago. Good questions. Okay, any other questions? Good, then let's continue with the second set of slides. That's also on that Google Drive, the handouts. It is descriptive statistics. How are we doing time-wise? 10 minutes. So this block goes until what time? Is it until
Until 4:30.
4:30? Okay, so 45 more minutes. Great, thank you. So now you can sit back, relax, because the review that later you will see, oh, semi-variogram is so similar to variance. Why have I ever worried about complicated stuff? No. So classical statistics is focused on the magnitude of observations. It quantifies population properties. It neglects spatial coordinates, and it neglects also temporal coordinates. So it is just based on observation. And we talk about different moments of the probability distribution. The first moment is the mean value. You all know the equation for the mean value. So all those individual observations summed up and then divided by the number of observations. And this is the arithmetic mean. Then the second moment of the probability distribution is the variance. And that is equal to the squared standard deviation, as you all know. And here we deal with sample variance that is calculated by summing up all the differences between each individual observation and the mean. And that is just done for a subset of the whole population. That's why it is sample variance. We cannot sample the whole population. And then we divide it, we take the average, but we don't have here all numbers of observation, but n-1 in the denominator. So that's how we get the sample variance, that are ordinarily called variance. And you have all used those intrinsic functions in Excel. In applied statistical time series analysis, the way we use it, we use a lot the so-called population variance, that is abbreviated with the Greek sigma. That's equal also to the squared standard deviation, sigma, from the mean. But here we assume this is representative of the whole population, so we can just divide it by n. That's called then the population variance. That's how it is referred to. And due to the lack of precise knowledge of the population variance, we need the sample variance. We work a lot in time series analysis and also in those time series packages that we will be using with the population variance. Then another thing, the coefficient of variation, you all know that also. It's a standardized measure of variance. Just looking at the variance, we cannot say whether a variable varies a lot or not. Just by looking at the magnitude, we have to standardize it, and that is done by looking at the mean value. So the coefficient of variation is the standard deviation divided by the mean. So the units X each other out, and it's a value normally between 0 and 1. In some cases, it can also be larger than 1, and some people express it as a percentage by multiplying this ratio by 100. It's a measure to describe the frequency distribution and used for comparing the variance of 2 or more different data sets. And if that coefficient of variation is larger than 1 or larger than 100%, we are inclined to say, or some erratic high values may be present. And a high coefficient of variation may be an indication that the arithmetic mean is not appropriate to represent the population. So we then need to run a test for normal distribution. We can use these statistics also for calculating the necessary sample size n. That's the number of samples that we need to take for a certain tolerable deviation from the mean value. So this will tell us, given a certain variance of the data, we need to take so and so many samples to have at some level of, at some probability level, have a reliable measurement. Frequency distribution, that is needed for determining the confidence limits and the knowledge of whether or not observations are normally distributed. Here is a set of 140 soil water content measurements. We have seen them graphed before. That is this data set. And we now want to look into their frequency distribution. Simple. So the mean is 0.126 and their standard deviation 0.01, both in volume fractions. And these were soil water content sampled along a transect that was 140 meters long at every meter. And I think the sampling was done by Keith Castle, who is now a retired soil physics professor in North Carolina State University. So a histogram, you all know what it is, right? We divide the range of observations into different classes. And for each class, we count the number of observations within that class. That gives us then a bar graph that we call histogram. How many classes do we need to choose? 440 measurements. How many classes would you take? I've chosen here how many? 10, I think. 4, 5, 7, 8, 9, 10, 11. 11. Is that a good approach or not? Mm-hmm. A good number to start is rule of thumb. It's no written law, but a good rule of thumb to start is the square root of n. So square root of 140 is more than 11. It's less than 12. I chose 11, so you also could have used 12. What if we have combine harvester data? Thousands of them. Of course, in that case, we do not take the square root of n. Then we have to follow other rules that I'm not aware of, but a significantly lower number. Why do we need histogram for combine harvester raw data? In order to process them. Machine data have a lot of false values, and we need to define criteria to get rid of them so that we can then work with a clean data set. So here are two different histograms for the same data set. First example, I used 8. Second example, I used 11. What do we do next with this? So we can calculate a probability density function, a nice curve. How is the curve called? The bell curve. And who created it? It was the good old mathematician Gauss. Gauss was a mathematician at the University of Göttingen. And he created, I've read a book about him, he created a lot of nowadays coordinate systems. So when we do the transfer from geographical coordinate system, latitude, longitude, into Gauss-Krüger coordinate system, that is metric, and we need to do that for doing spatial data analysis.
It is also called ogive curve.
Ogive curve? I've never heard the term. Thank you. I need to write it down after the lecture. I need to write that down. Thank you so much. And we can create this curve by and have the number of observations calculated. And these are the individual components of that curve. We will do that also in an Excel exercise for one data set, not for this one, for another one. We will use this equation, and the components are the upper one is the estimated number of observations of water content at a magnitude, and this is then the number of sampled values in the entire population. And the delta theta is the class width in which we divide up the data range. So, and that's calculated maximum number minus minimum number divided by number of classes. We will do that in Excel and then use that that information for calculating the different classes. And then population, S is the population standard deviation, and sample mean is here. We need both. And the farther or the smaller we take the number of classes, sorry, the class width, the more classes we have, and that will then, of course, change the shape of that bell curve, but it will be always adapted to those histograms. So this defines the width of each class. We cannot vary both independently, and then we will get the respective curve. So that's how we get this bell-shaped curve, and it fits the histogram. And we can say in this case that the values of measured soil water content are normally distributed. We have a test that we will also learn in R about that, the Kolmogorov-Smirnov test. And how many observations are necessary to estimate the mean value of theta that can be derived for a desired level of probability from this histogram, from this bell curve? The next one is the fractal diagram. There's not so much flexibility. The fractal diagram is a fractal diagram. We don't have to make any choices of classes. The histogram depends on arbitrarily selected class width. The fractal diagram is a cumulative frequency of observations versus their magnitude. And this is a plot of it. Nowadays, it's all in R. It has a different name, quantile plot or so, but it's basically the same. There was, when I studied this first, there were no good algorithms for it, so I used from the old Fortran numerical recipes book. I used an algorithm for calculating these, and so here's a short scheme that I have drawn here for you, but we can also easily nowadays use an intrinsic function in Excel. That's what we will be doing in the class, then in the exercise, to come up with a fractal diagram. So we first need to arrange the observed values in the order of ascending magnitude, then calculate P from the theoretical cumulative probability, and a perfectly normally distributed data set follows then a theoretical distribution. And this is the cumulative probability. And here's the standardized deviation. So it's all in standard deviation units. And this is described with this function, where beta is the function, and when u turns to infinity, the area under the curve approaches 1. And that u is calculated z minus the mean value, so observation minus mean value divided by population standard deviation. We can then plot the data either on probability paper or use standardized deviation plot. This is my old routine I had used just for, this is a museum. That's the way how we programmed things in those days. I'm still a frequent Fortran user. Here is a table of this cumulative probability from Davis, a very good statistics book. This is all in units of standard deviations and the cumulative probability. So we can use this as a table and still interpolate in between. Or now we have this norm.inf Excel intrinsic function. We give these parameters. Since it is normalized, we use 0.5, and then the mean is 0 and the standard deviation unit is 1. And then we get our U values and we can plot those and get the diagram here. And that's for those 140 water contents. And we can see what the histogram indicated already. They follow a nice straight line. Here are all the water contents, and here is their probability level here in units of standard deviations. And they are not perfect because there's scatter in the data. And the deviations for this data set are the highest at both ends of the data. But that would not be strong enough to say the data are not normally distributed. I also want to point you at the fact how simple statistics of this data set are related to the regression parameters for this line that we calculate here, and we could simply calculate in Excel the regression coefficients A and B. So U is equal to A times theta plus B. B, now I draw a blank here. So A is the slope and B is the intercept. And B as the intercept is equal to minus mean value divided by standard deviation. And we have calculated that here. So this resulted in 11.85. And if we take these values here, then we get minus 12. So they are very close to each other. And A is equal to 1 over standard deviation. So the slope gives 1 over standard deviation. That is 0.0101 over 0.0105. So data are normally distributed if they fall on a straight line, and there are tests of linearity called Kolmogorov-Smirnov. And what if they do not fall on a straight line? What can we then do? And we can ask ourselves, are the data log normally distributed? Have you ever worked with non-normally distributed data? What were those variables? Have you ever measured saturated hydraulic conductivity? Well, so remember when you do that test and they are not normally distributed, you can use transforms. And the log normal transformation is not the only one that you can use. There are tons of transformations available. If data are really not transferable into a normal distribution, like heavy metal concentrations. They can be a headache, or environmental contaminants. You have a point source where the magnitude is tremendously high, and then you have an area where the rest of the observations is way lower orders of magnitude, and there's no way to transform those. You never get them on a normal distribution. You then work with non-parametric statistics. So you work with their ranks, for example. I once had a tracer experiment on transport. These were the chloride concentrations, and as you can see, they were obviously not normally distributed. So we then log transformed them, and here is the plot of the log transforms, and fortunately that transform made them look more normal. So we now get to next higher moment. So remember, we had the first moment, the second moment, mean and variance, and now we come to other moments. That's a mode median. Mode is the range of the most frequently measured value. So we can identify that from the histogram. Median is the midpoint of observed data. 50% of measured values are larger and 50% are smaller. And they are not much influenced by extreme values. And the normally distributed data sets have mean, mode, and median being identical or close to it. Another one is skewness. Has anybody of you used skewness in their analysis? And what data is that? Sorry, long term?
20 years rainfall data. That have classified that rainfall data into different seasons.
Mm-hmm. Okay.
So that I will calculate the experience and the season.
Good, good. And what does the skewness tell you? It characterizes the asymmetry of the distribution. Right? So the symmetric distribution gives us a skewness coefficient of 0. And it's just computed very similarly as the variance. We have just a 3 here in the exponent and also a 3 here. So that's called the third moment of the probability density distribution. And if the skewness is highly affected by extreme values, the sign is important, not necessarily the magnitude so much, but if if the skewness is positive and the median is smaller than the mean, then we have a longer tail to the right hand of the histogram, and it occurs in case of physical reality limiting the values close to the range of observations. Then we have a coefficient that is kurtosis, and that is very ambiguous by Excel. So the original definition of kurtosis is this way. What you obtain from Excel when you type in the intrinsic function for kurtosis is kurtosis. It is the excess. Those are very similar, but not the same. So the coefficient of excess is kurtosis minus 3. So if the kurtosis is in the range of +3, then you can relax, then everything looks normally distributed. It shows the extent of the peakedness or flatness of a data set, of a distribution. So a normal distribution has a coefficient of kurtosis equal to 3. If it is more peaked, it's a kurtosis larger than 3, and if it is flatter, then it is a kurtosis less than 3. So don't mix it up with coefficient of excess. I've put together a few programming lines in R when we calculate the moments. So don't be surprised when you get the Excel answer for kurtosis. But it's wrong. It is not kurtosis. It's excess. And Excel uses n-1. And also for S, it uses the sample variance, not the population variance, as we will be doing it. So here, now the complete set of statistics for this curve, mean, mode, median, all very similar, skewness and kurtosis. So now we will move over to some actually measured data. These are water infiltration rates that were measured at every meter. I think it was a graduate student of Dr. Nielsen. And here's the histogram of the water infiltration data. This is very common. Hydraulic conductivity, water infiltration rate, in some cases also diffusivity data, percolation data. They are rather non-normal distributed than normally distributed. So then we have to work with transforms. Here is the fractal diagram for the infiltration data, and here is the fractal diagram based on a log basis of the infiltration data. And here we can calculate, even for this non-normal data set, we can calculate the bell curve, which does not look anymore as a bell curve, but this is the form of a bell curve. These graphs and those equations are all in that book, and of course you have them all in your handouts too. So you can apply these to your own data sets. Now here I want to introduce you to a data set that we will be working with a lot. That is from a data set from Mohammed Baza. He was a graduate student in Department of Land, Air and Water Resources in Davis, California. And he was interested in the effect of irrigation water salinity level on soil surface temperature. What would you say is the relationship of, or the impact? What would be the hypothesis that you follow when you study the effect of salt level of irrigation water and surface temperature? So you can imagine that there are experimental fields, strips. This is only a zoom in, so the same strips were here in the different replicates. So different levels of salt concentration of the irrigation water were used in this sequence. And now the water is gone, water is drained. Of course, the salt is still present there in the surface soil. So what would you now expect the temperature to be? Is the temperature higher in the high or the low salt? So is it a positive relationship between salt level of irrigation water and soil temperature, or a negative relationship? Negative. Why is that?
Because the oil temperature is higher, we are irrigating with due to higher temperature, the salts which are present in the irrigation water start settling, thereby it increases the salinity level of the soil.
Wow, good, great explanation. Here are the surface temperature data that he collected in these plots, and behind each of these symbols, each of these 64 points, there are, there are 36 individual values. That's that one average then. So he had to take about 2,000 measurements in a day. And of course, when you start measure, so he had an infrared gun and he had all his points marked out. So he then took those measurements, but it took him a day roughly. So what do you do then? There's a event with the sun. So in order to compensate and make it then manipulate the data set in a way as if he had taken them all in one shot in the same minute, he had to go back to certain points during the day and measure them again. And then he could correct out that trend that was affecting his measurements during the day. That's a good strategy, I think. But everybody in the department got mad at him because he got all his data for his PhD thesis taken in one day. Yeah. It took me more. It took me about a year for getting, if I accumulate all the measurement times. Yeah. And then that's not even enough. His thesis was awarded the best thesis answering a statistical question outside of the statistics department. So here's the soil surface temperature histogram for the data, and you see way too many classes. Instead of 8, or instead of these many, I should have used 8, but so be it. This is for the north-south direction, and this is the fractal diagram. And for the soil surface temperature in the east-west direction, that is when we look in this way. So all the variability is averaged out in each of these values. We can see that here. So all the variability is x'd out by averaging it. Here's the histogram for it. Way smaller range. Fractal diagram. And outliers. Outliers are suspect observations. Have you ever dealt with outliers? What do you do about outliers? Is there measurement error? Is there resampling possible? For some lab measurements, yes, you can do. When we have a bad clay content in our data that is obviously wrong, then we still have some soil left, and then we run the analysis again, hoping that then we get the right result. But oftentimes, for example, for field observations, that is not possible. Oftentimes, there's this, and we apply that same limit, we apply that to combine harvester data by cleaning them, ±2 or ±3 standard deviation. Everything larger and smaller than that, we throw out from the analysis. So here in this case, this point would have probably gone out, and this, and this, and those are outliers. So the fancy statistic programs will certainly have an option, or we look up in the help menu, replacement of outliers. Yeah, there's an algorithm for that, and we can do that. So we will look at this data set again when we work on autocorrelation and cross-correlation, and also when we work on spectral analysis. Now we want to briefly look into covariance. You all have dealt with it. It is the beginning step of correlation. And it's the joint variation between two variables. It depends strongly upon the magnitude of y and z, and therefore it's not easy to use as a measure of how close two variables are related. Therefore, we use the normalized covariance, that is the correlation. Simple covariance divided by the product of the standard deviation of both variables. Here, we took mineral nitrogen samples in a farmer's field in 2 subsequent years, 224 locations, down to 90 centimeter depth in 3 compartments. And here are the distributions for both the histograms. The means differed. It's both after harvest. And here we wanted then to calculate a linear regression. So step by step, if you haven't done so, well, nobody normal would do that by hand, but I've put out here the equations for calculating a correlation. So we want to calculate these regression coefficients, slope and intercept. And I don't need to read you all these equations here, just the deviation is at minimum, deviation between estimate and measured value. So here we go. You can all run that in Excel for the data, and this is then how the correlation turns out. The regression relationship, big flaw in this figure. What is wrong in this figure? What's wrong in this figure? Never draw the line outside the range of your observations. And then we came up with A and B, those coefficients, slope and intercept, and then the covariance and the normalized covariance, and we got the correlation and the R-square value for both sets. That's the answer then to it. What else do we have? So from the calculation of regression coefficients, it becomes obvious that we apply a constant mean over the entire range of observations, and deviations from the regression are assumed to be normally distributed, and sampling locations are ignored. So here we also did the mathematical exercise. That's for the case of the trend data, elevation versus distance. We just calculated also a linear line, and then we can use it later for detrending elevation data. We can also do something for those erosion plots. Here, we want to calculate the correlation between soil temperature and salt level of the irrigation water plots. And yes, you were right, negative relationship. So here's the R square, 0.3. And again, the line, bad, bad, bad. Saturated hydraulic conductivity and porosity at every meter sampled along a 100-meter transect. So NK sat, already log transformed, and then porosity here. Low relationship. Does that surprise you? Porosity and conductivity should be related, right? No, porosity does not say anything about pore size distribution. And it's Hagen-Pore soy who makes a big mark on it. The pore size distribution is the trigger of transport. The pore size distribution and the tortuosity of pores. That's why we never can get a good relationship between porosity, total porosity, and conductivity. It is assumed so by for many modeling studies. And you also know that porosity is directly linearly related because they depend to bulk density. And there are a bunch of geographic studies, regional studies, where people needed to parameterize a region with hydraulic conductivity information, and they derived from soil type, they derived the bulk density, and then from the bulk density, they derived the porosity, and then from porosity, they derived conductivity. So many derivation steps can't be right. And I think that is dangerous. We can do better than that. Okay, that ends the set on descriptive statistics. Any questions about this set of cartoons, of slides? Was it all known to you? Did I tell you something new? No, right? Just here's question number 1, and then your number 2.